Today I'll give you a tutorial slash overview of different three-dimensional imaging techniques. And if I could steal the mic, that would be helpful. So in my talk, I'll discuss both linear and nonlinear optical processes that can allow us to do three-dimensional imaging. And in particular, in terms of techniques, I'll discuss multiple harmonic generation, the broadband, coherent anti-Stokes Raman scattering microscopy, and stimulated Raman scattering microscopy, as well as toward the end of the lecture, I'll introduce the concept of optical tracking and its realization in the form of holographic optical tweezers that can be then integrated with the nonlinear optical imaging techniques. So the idea is that using light, we'll be able to do both three-dimensional imaging and three-dimensional non-contact optical control of different liquid crystalline systems and composite systems that involve liquid crystals. And so this will be a continuation of a very nice lecture given today in the morning by Professor Rosenblatt, where he used ENSO for nanoscale three-dimensional optical imaging, as you remember. In terms of imaging of liquid crystals, I think by now, because we had a couple brief introductions to polarizing optical microscopy, you're all already familiar with the main concepts that are used in this technique, right? So all we need to have here is an optical microscope with two cross polarizers, and then we will observe textures of this kind that in many cases would be sufficient for us to understand the director structure behind those structures, right? Because, say, having an image of this kind, we could figure out two-dimensional director field corresponding to it, and we know optics that's behind this type of imaging. But this now brings me to a clicker question to see if indeed you were able to follow the previous lectures we had and know what do those kind of images tell us, right? So remember, in the previous section we had those dark brushes. What do they correspond to? All right, so I see people vote. This should be a fairly simple question for you, so don't take too much time for that. Only 50. I'll have to stop at some point. Okay, I'll stop. So let's see the distribution. C, the regions with in-plane director along polarizer or analyzer, and that's indeed a correct answer. So good, it looks like you're not sleeping, at least not now because you voted. Alright, so now how about three-dimensional imaging? It's a little bit more complicated if we have three-dimensional director fields, because from the polarizing optical microscopy that we just discussed, you realize that in this expression for intensity in the polarizing optical microscope, we have an integral, and we cannot really easily resolve the structures across the sample thickness because light is passing through it, and then the signal that we get in the end is a two-dimensional texture that's somehow related to a complicated three-dimensional director field. Now, many years ago, we introduced the fluorescence confocal polarizing microscopy, which is a little variation of confocal microscopy technique that allows for a three-dimensional patterning, imaging or mapping of director fields in liquid crystals. And just like conventional confocal microscopy techniques, it utilizes dyes that are doped into liquid crystal as small quantities, except that those dyes are anisotropic molecules, very similar to liquid crystal molecules themselves, and also the imaging is done using polarized, typically linearly polarized excitation light. So now, because of those two little differences compared to conventional confocal microscopy, we will not only be able to resolve things across the sample thickness, that's a feature that conventional confocal microscopy already provides, but also the fluorescence signals that we will detect will be orientation sensitive, right? Just because the transition dipole moments of the dichroic or the fluorescent dye molecules follow liquid crystal director, and the intensity of fluorescent light will depend on the angle between liquid crystal director and polarization of excitation light, right? And so if we excite the dye molecules in liquid crystal, using a setup schematical as shown in here with laser light, then in epi detection mode, right, we can detect fluorescent light that will go backward through the same optics, and then will be passed through the confocal aperture in here, the pinhole. And this pinhole plays a very important role in here because it allows us to reject all light that comes from above and below the focal plane, right? That's why we call this technique, which originally was introduced some 60 years ago or so, confocal microscopy, right? Because those two planes are confocal with respect to each other, and this principle allows us to obtain resolution not only in the plane of the sample, like most of regular microscopes do, but also across the sample thickness or along the optical axis of the microscope. Now, the question is, how do we find all kinds of dyes that would work with all kinds of liquid crystals that we could possibly have? And as I already mentioned to you, one of the requirements is that we typically want to have a transition dipole moment parallel to the long axis of the molecule. Also, we need to have absorption and emission spectra separated from each other so that we could use interference filters and separate absorption and fluorescence and use excitation laser light in here to excite those dye molecules. So the question is, would it be possible to do imaging of liquid crystals, at least in some of the cases, without the use of dyes? And the answer is yes, and it should be possible because liquid crystal molecules themselves contain aromatic groups like this two benzene rings in here in the central part of familiar to you molecule 5Cb. They also contain many other chemical bonds that could be utilized for three-dimensional imaging using nonlinear optical techniques that I'll discuss during the remaining part of my talk, right? So if we take a three-dimensional texture, and the simplest one perhaps is this texture around a point defect in liquid crystal, the hyperbolic point defect you see here, you would realize that those lines of director field represent nothing else but local average orientation of liquid crystal molecules. And so if liquid crystal molecules follow those director field lines, we could tell what those director field lines are, provided that we would know how the CN chemical groups, triple bonds are oriented, for example, right? Because they are along the director field on average. Also, the transition dipole moments of fluorescence corresponding to those benzene rings in the 5Cb molecules, right? So we can use a number of different approaches. Multiphoton fluorescence or simply fluorescence imaging that involves the liquid crystal molecules themselves instead of dyes. or we could use the chemical bonds like CN chemical bonds, and as we would look at more complicated molecules than this simple 5CB, we'll find even more useful different chemical bonds to probe the orientational structures of director fields and liquid crystals. And so before we proceed with that, I just want to remind you about multiphoton excitation or multiphoton absorption processes, right? So typically when we have dye molecules or molecules like liquid crystal molecules, we can have single photon absorption, right, where we can excite those molecules by absorbing the light at certain frequency, and this process is illustrated in here. However, we can also have multiphoton excitation processes where where we can absorb two different photons at wavelengths which is twice the wavelengths of absorption of a single photon, as you see depicted in here, and then the emission of fluorescence will be in roughly the same spectral range as that what we see for a single photon absorption process, right? And so you can see both of those processes illustrated in here. This corresponds to single photon process and classical, and here you can see two photon absorption process. This would be better to reverse. Now the question is, can we always observe both of those processes easily enough to do three-dimensional imaging? And you will see from my discussion that will follow next that we will typically need pretty high intensities of light or powers of laser beams in order to have this multiphoton absorption, right? So it can only take place if you have pretty high intensity, because the probability of this process is very low. So you need pretty high laser powers, but the big advantage that you can see by looking at the fluorescence pattern corresponding to the two photon absorption process is that it's three-dimensionally confined, right? Because intensity of fluorescence light coming from this spot is falling very quickly, not only in the plane perpendicular to the optical axis of the microscope, but also along the optical axis of the microscope, right? And so now, if we were to use multiphoton absorption process in fluorescence imaging, the big advantage, therefore, would be that we would not need a confocal pinhole at all. So it would not be confocal imaging, but will allow us still to obtain three-dimensional resolution, just like in the case of confocal microscopy, right? And so this schematic in here depicts the difference between the two different processes. So in the case of a single photon absorption process that would be used for fluorescence imaging, we typically excite the sample with light at shorter wavelengths and detect emitted light at a longer wavelengths. It's opposite case for the multiphoton fluorescence imaging, right? We will be exciting at a longer wavelengths, but detecting fluorescence light at a shorter wavelengths because, as I already mentioned to you, the wavelengths of light in the two photon absorption process is roughly 2 times that of the wavelengths of light that you would need for single photon absorption process, and the frequency is therefore 2 times smaller. Right, so now I already, however, mentioned to you that the challenge is to have those high intensities of light or high laser powers, because the probability of multiphoton absorption process is very low. And so in order to achieve this, we'll be using pulsed laser light, right? Because although, as you can see from those little estimates I have on this slide, and I'll not go through them because they are very obvious, I hope. Although we will have very high instantaneous laser power in the pulse laser beam, the average laser power to which the sample will respond in terms of not overheating, not burning things, the average power will be low, right? And so, however, having this instantaneous laser power or intensity very high will allow us to have high probability of multiphoton absorption processes. And this is quite important from the standpoint of view of liquid crystals, because although instantaneous laser powers that we will be using will be quite high, the average power will be low, and we will assure this way that we do not realign liquid crystal director as we try to do imaging in 3 dimensions. So here is a schematic that is telling you the basic principles of multiphoton absorption and fluorescence processes. If we take a molecule like 5Cb, right, and now I'll use this particular example, this molecule would act as a dye if you were to excite it at 327 nanometers, as an example, right? You could do it at shorter or slightly longer wavelengths, it would fluoresce as well. However, you might know that excitation in the UV part of optical spectrum is very difficult because you would need very special optics to do that. And so it's not convenient for this reason. To do it, it's also quite expensive. Instead, what you could do is you could do 2-photon excitation of the very same molecule at 654 nanometers, right? That would be equivalent to this single photon process here. Or instead, you could use 3-photon absorption process at 981 nanometers, right? And so in all of those cases, regardless whether you use 1-photon, 2-photon, or 3-photon absorption process, we would always get emission in the range, roughly same range, from 400 to 450 nanometers. Right now, doing the excitation in visible or near infrared part of the spectrum is much easier than in UV, especially in near infrared, because this will not also interfere with the detection of the fluorescence light, right? So it will make our life easier. Now, just like in the case of a single photon absorption process that we could use, say, in confocal microscopy, in the case of multiphoton fluorescence imaging, we'll have very strong orientational sensitivity. Apparently, if we go from linear processes to nonlinear optical processes, this sensitivity becomes even stronger, right? So if we were to have 5Cb molecules in the liquid crystal following director parallel to polarization of the excitation light, we'll have very strong signal coming in the form of fluorescence. Whenever they are perpendicular to each other, the signal is expected to be very weak, and then we'll have some angular dependence in intermediate cases, right? So this angle alpha will determine what kind of a signal we get. Now, if you were to simply estimate the kind of angular dependence we are expecting all of those cases, single, 2-photon, 3-photon, multiphoton absorption processes, you would realize that whenever we use unpolarized detection of fluorescence light, the dependence will be of this kind, right? So will depend on intensity of excitation light, but then we'll have cosine to the power 2i of alpha, where I in here is nothing else but the order of nonlinear optical process. So if it's single order linear absorption, then this would be just 1. It would be 3 for 3-photon absorption process. Right now, if we were to detect light, the fluorescence light through the polarizer as well, then we'll need to add 1 in here, and this dependence becomes even stronger. So you can see that going from linear process to nonlinear process, we further increase the angular dependence of the fluorescence light, and this would allow us to do better detection of director fields patterning and visualization of director fields in liquid crystals. So this is what relates to single photon and multiphoton fluorescence imaging of liquid crystal director fields, but I've shown you that we could also utilize the presence of chemical bonds, like for example CN chemical bond in the 5Cb liquid crystal molecule. And so to do that, we could use, for example, Raman scattering, right? However, all of us know that Raman scattering is an extremely weak process. So it's good for spectroscopy, but it's not too good for three-dimensional imaging because you would need to accumulate signal for quite long periods of time in order to obtain good enough image, right? And so, however, the big advantage is that it tells us pretty much all information about the structure, chemical structure of liquid crystal molecules, because you can find signatures, features corresponding to all different chemical bonds of the molecules of interest. And so it's kind of complementary to infrared spectroscopy as well. Right? So this is a diagram describing the Raman scattering that you might be familiar with, but as I already mentioned, if you use a linear Raman scattering process, then the Stokes and anti-Stokes light that we would be detecting would be very weak, in the order of 10 to minus 10 photons per single photon incident on such a chemical bond. And so this is obviously not very good from the standpoint of view of imaging. The question is, can we use nonlinear optical processes to enhance Raman scattering to obtain much stronger signals and yet have the very same information as we do in the case of Raman scattering that we typically use for spectroscopy? And the answer is yes. So one technique that was developed and originally introduced for biological research is stimulated Raman scattering microscopy, which we again adopted for imaging of three-dimensional director structures in liquid crystals. Right? So now, in order to probe the structure of liquid crystal director fields, we will use femtosecond pulsed laser light, this light will be at two different frequencies, the pump frequency and Stokes frequency, that you can see depicted in here. On top of that, we'll be modulating the Stokes signals using electro-optic modulator. And then, as we will be modulating the Stokes signal, we'll be probing the transmitted light at the pump frequency. And so we'll be looking at modulation of pump signal. Right? So here is a schematic, very simple, highly oversimplified visualization of how we implemented this technique, right? So, as I already mentioned, we use spatial light modulator in order to spectrally shape the femtosecond laser light, and we also use a photonic crystal fiber. Combination of those two allows us to obtain femtosecond laser light at different frequencies that is then introduced into the liquid crystal sample somewhere in here on the optical stage of the microscope. And also what we do is we modulate, using this electro-optic modulator, the Stokes signal as depicted in here. Right? So then both of the signals are spectrally and temporarily and spatially overlapped in the focal point when we focus this laser light into the liquid crystal sample somewhere here, and then we detect the pump signal that is modulated because of presence of Stokes signal at the very same time in the liquid crystal sample. As we do it, we then can use a lock-in amplifier and recover the information about orientational structures and director field in liquid crystal samples. In addition to that, we can also do coherent anti-Stokes Raman scattering imaging that I'll discuss next, and the principles behind this type of imaging. But before I do that, let me give you a very brief introduction to the coherent anti-Stokes Raman scattering spectroscopy and microscopy at the same time. In this process, we typically use, just like in the case of SRS, or stimulated Raman scattering, we use pump and Stokes frequencies, and then the beating frequency corresponding to the difference of the two is matched to intrinsic vibration frequency of the chemical bond of interest in the liquid crystal molecule that's comprising our liquid crystal sample. Then, unlike the stimulated Raman scattering, which is second-order nonlinear optical process, the CARS, or coherent anti-Stokes Raman scattering, is third-order nonlinear process, and we can detect this anti-Stokes Raman scattering at the frequency corresponding to 2 omega p minus omega Stokes, right? So those are the excitation frequencies at two different cars. And so as we do it, just like in the case of multiphoton fluorescence, we will now have very strong angular dependence of detected Raman scattering signal, both in the case of SRS and CARS, and we can utilize this angular dependence to reconstruct the director field structures. Right, so now, in addition to simply using the excitation laser light tuned to single frequencies and detecting information corresponding to individual chemical bonds, we can also do broadband coherent anti-Stokes Raman scattering imaging because one can use broadband signals to a Stokes signal, for example, as depicted in here, and then we'll be detecting broadband coherent anti-Stokes Raman scattering signals, and this will contain information about orientations of not just one chemical bond of interest, but multiple different chemical bonds that could be of interest. So, as I already mentioned, coherent anti-Stokes Raman scattering is a third-order nonlinear process. It depends linearly on the intensity of Stokes light, but quadratically on the intensity of pump probe excitation light. And altogether, as you can see, it's intensity of excitation to the power 3, as you would expect for third-order nonlinear process. This particular technique was introduced as imaging technique, although spectroscopy was known back from 50s and 60s, but as an imaging technique it was introduced in the end of 90s. Now in here from the dependencies of CARS signal on the excitation intensities of femtosecond laser light, pulse laser light, you can see that indeed we have quadratic dependence on pump probe intensity and linear dependence on Stokes intensity. Now, the big advantage of using CARS or SRS or multiphoton fluorescence, as I already mentioned, is that we can do excitation in the infrared part of spectrum, but detect the light in the visible part of spectrum, and therefore this makes it easy to implement, but at the same time, penetration, as many of you know, of near-infrared light in scattered media, highly birefringent media, is better than that of visible light, and this therefore is providing important advantages as well. So the coherent anti-Stokes Raman scattering technique can be implemented in many different ways. I'll show two different examples. So in here is one of the examples, depicted using this schematic, where we can use two different lasers. In this case, of picosecond laser excitation light. Then they are both combined and brought to the focal point using a number of different mirrors and optical elements, and then focused in here. Then, as they are spatially and temporarily overlapped, we can detect light in forward detection mode, the coherent anti-Stokes Raman scattering light in forward detection mode, and also in epi-detection mode, the light that, just like in confocal microscopy I was showing before, will be propagating in the backward geometry. And in both cases, both forward detected and epi-detected coherent anti-Stokes Raman scattering signals can be used to tell about the composition of your sample. If it's liquid crystal mixture, you could probe whether the different components mix well or separate. If it's a liquid crystal, say of nematic type or cholesteric type, you can probe orientational patterns of corresponding director fields. But as I already mentioned before, in addition, unlike in the case of technique that I just described on the previous slide, we can also implement coherent anti-Stokes Raman microscopy in the broadband version, where we can use single frequency pump laser light for excitation, but broadband Stokes excitation light, and then we can detect broadband coherent anti-Stokes Raman scattering signals. So in here you can see the excitation, the pump light and the Stokes light corresponding, the broadband Stokes light corresponding to this kind of a diagram, right? And then we can detect the coherent anti-Stokes Raman scattering signals that would be obtained using those excitation laser beams. So this is a schematic that depicts how this is actually realized. So, and again, there are many different approaches that could be used to obtain CARS and SRS signals, but one of them we depict in here. So we utilize a TISA 5 femtosecond laser source, and then we can also utilize a photonic crystal fiber in order to obtain supercontinuum femtosecond laser light in the output that is then spectrally shaped using liquid crystal spatial light modulator, so that we can bring different laser frequencies to the sample where we focus this laser light and overlap temporarily and spatially. As we do it, we then detect the CAR signals and SRS signals in both epi-detection and forward detection modes using photomultiplying tubes that you can see depicted in here. And so this brings me now to a clicker question, which is based on what we discussed but some minutes ago. So I turn the system on. Okay, I'll stop in a couple of seconds, so try to vote. soon as you can. Only 48. All right. So majority answered E, and that's indeed the correct answer, right? So I described to you a number of different nonlinear optical processes that we can use for imaging, and all of them are very helpful in terms of getting as much information about the liquid crystal director structures as possible, and they would not be possible to, it would be impossible to realize them without femtosecond laser pulse laser sources, picosecond or femtosecond laser light, just because in order to achieve nonlinear absorption or any of those other processes we discussed, we would have to use so high laser powers of continuous wave laser light that we would simply burn the samples, right? Now, however, by using femtosecond or picosecond laser light, we can avoid this process, we can avoid those problems, and on top of that, we can also utilize, we can also achieve better resolution, better orientational sensitivity, and so on. So in here you can see pictures showing how those techniques are realized in our lab, and the important thing to mention in here is that you can realize all of the techniques we discussed at the very same time on the very same optical table, integrated with the very same microscope, and the techniques that we discussed also provide complementary information, right? So if you probe orientation of chemical bonds, or if you probe orientation of transition dipoles, fluorescence transition dipoles corresponding to liquid crystal molecules, you combine this information together and you learn it more about the sample than what you knew about it before of what you could learn by using just one of those techniques alone. Next I will, and so those are all just pictures showing realization, particular realization that we had where we integrated all of those techniques at the very same time. So now next I'll proceed with showing you a couple examples of nonlinear optical imaging of different liquid crystal samples, and then I'll show how we can integrate those nonlinear optical imaging techniques with optical manipulation and not only be able to visualize director structures in 3D, but also control them non-destructively by non-contact optical control. So one of the molecules we probe is 8Cb. This is a molecule that forms symmetric liquid crystal phases, as you know, and if you were to take a Raman spectra, it would look like this, where you can see the two spectra for two orthogonal polarizations of light, parallel and perpendicular to the liquid crystal director corresponding to, for excitation of laser light, parallel and perpendicular to the liquid crystal director. If we, instead of regular conventional Raman scattering, obtain coherent anti-Stokes Raman scattering, say corresponding to this peak, this is peak corresponding to CN chemical bond, we can obtain Carr spectra, this is just this very region in here, and you can see that the signal now is many orders of magnitude stronger compared to the conventional Raman scattering process. On top of that, it's also much more orientation sensitive, right, this process, because you can see that now the dependence on orientation of excitation laser light is much stronger, and both of those features are very helpful in terms of three-dimensional optical imaging. We can take, we can measure orientational dependence of the Carr signal as a function of the angle between director and the polarization of excitation femtosecond or picosecond laser light. And so you can see that it's very strong dependence. For example, for the case if we use Carr's imaging and we use a polarized detection where polarizer is parallel to polarization of excitation femtosecond or picosecond laser light, we have this dependence of the order of cosine to the 8th power of theta, where theta is the angle between director and polarizations of the excitation light and the detected Carr's signals. So with using those techniques, we can visualize different three-dimensional director structures. And so in here is one example of a focal conic domain that was imaged using coherent anti-Stokes Raman scattering microscopy. The image depicts only one plane corresponding to the plane of ellipse, and by stacking together many such images into three-dimensional image, we can then visualize such a three-dimensional director structure. And so you can see three-dimensional coherent anti-Stokes Raman scattering images obtained in this mode corresponding to the focal conic domains in here, and the corresponding director structures as well as layered structure of the focal conic domain. Right, so you can see that this focal conic domain sits with its elliptical plane on the one of the confining glass plates of the liquid crystal sample. Now, since we are somewhat running out of time, I will rush a little bit through a couple other examples, but just to illustrate principle, I want to show next that we can use together those different imaging techniques we discussed. Right? So if you were to take, say, a colloidal particle and liquid crystal and put it inside of smectic liquid crystal, as for example in this case, then you can detect all the signal that you get from the sample as you would excite it with the pulsed laser beams. And so you can see that we can have both Carr signals and we can also have 2-photon and 3-photon fluorescence depending on whether we use fluorescent dye or not. So if we detect the fluorescent signal corresponding to HCB molecule itself, then we will, we'll have this spectrum corresponding in here. And then we can use interference selection filters to assure that we will be probing, say, Carr signal corresponding to one particular chemical bond of interest, like CN triple chemical bond, and visualize orientation of those chemical bonds in the liquid crystal sample in particular. So in here you can see images of very same part of the sample with a colloidal particle in it, and the distorted director structure and layered structure depicted in here. In this case, visualized in 3-photon self-fluorescence mode. No dyes used, the fluorescence is coming from the HCB molecules themselves. In this particular case, we visualize distortions of the director structure and layered structure around the colloidal particle using coherent anti-Stokes Raman scattering, and we can visualize the particle itself using 2-photon absorption fluorescence signals coming from the dye molecules that are localized within the colloidal particle itself. Right? So by combining all of those different types of signals together, we can learn more about the structure than what we possibly could by using only one of those techniques. So here's another example of a layered cholesteric structure where cholesteric layers are parallel to substrates and helical axis is perpendicular to the glass substrates. we can see some defects in the layered structure, and this image is obtained by means of two-photon fluorescence polarizing microscopy, where we dope this sample with a dye similar to that used for confocal imaging, VTVP, but we can also obtain this information in the very same way from the molecules of liquid crystal themselves. If we simply detect three-photon fluorescence signal in this spectral region here, and we can obtain the very same information from Carr signals if we detect the Carr signals corresponding to the CN chemical bond in the liquid crystal molecules. So now, in addition to the multiphoton fluorescence and Carr's and SRS imaging techniques, we can also do multiple harmonic generation in the liquid crystal samples that are non-central symmetric, like symmetric C star. In this case, we can obtain strong second harmonic generation corresponding to the wavelengths 2 times shorter than that of excitation laser light, or at frequency 2 times larger than that of excitation laser light. And so in here again we can see that the very same sample can be imaged by means of three-photon fluorescence imaging for different polarizations of excitation laser light, as well as by means of second harmonic generation imaging, and we can then overlay fluorescence images corresponding to the different excitation polarizations of excitation picosecond or femtosecond laser light in order to reconstruct the director fields. So I'll skip, the slide which I meant to discuss the imaging of biaxial, different types of biaxial liquid crystals when we can have more complicated molecules. But next, before we go for a break, I very briefly want to introduce the laser tweezers. And so because we already had a couple introductions, I will be very brief. So when we tightly focus laser light, we can use optical gradient forces to localize colloidal particles or other inclusions in the region of tightly focused laser beam. And then by moving this location, by moving the focused laser beam, we can manipulate liquid crystals, defects, and colloids, and in the process of three-dimensional optical imaging, in the process of laser trapping, it's important to have strong enough gradient forces so that colloids or other inclusions can be entrapped in the focal point of the tightly focused laser light, and then we can manipulate those particles or other inclusions. Now, in order to be able to work with not just single but multiple particles, there are two different approaches. One is to quickly scan the focused laser beams between different locations, and by means of that manipulate multiple particles, or otherwise it's possible also to use spatial light modulators to manipulate the high intensity regions in the focal plane of the sample, and with that manipulate multiple colloidal particles, right? So for example, in here you can see an example from this article in here, where a grating was used to obtain intensity distribution pattern in the sample, and then multiple particles were entrapped using this intensity profile. Now, the nonlinear optical imaging techniques that we discussed, shown here in a simplified version on the left side of the schematic, can be integrated with holographic optical tweezers Then those techniques can be used at the same time. So one can manipulate colloidal particles as well as image the liquid crystal samples, for example, in which they would be incorporated. In this particular case, you can see that the laser tweezer system is integrated with the very same inverted optical microscope as the nonlinear optical microscopy that allows us to visualize those different samples. What I depict in here is that we can manipulate colloids and defects in liquid crystals and at the same time image them in 3D. So in regular microscopy, one would have a hard time knowing what happens with those two particles by just simply using them, looking at them in a conventional microscope. But this combination with three-dimensional imaging techniques allows us to visualize what actually happened as we manipulated those colloidal particles in liquid crystals. And this type of manipulation in three-dimensional imaging can be extended to other nonlinear optical imaging techniques and also other kinds of particles. Like, for example, in here you can see nanowires of gallium nitride that are being manipulated and imaged in 3 dimension in a cholesteric liquid crystal sample. And so you can see as the particle moves across the sample thickness, we can visualize it in there using different approaches. In this case, the car signal comes from the liquid crystal sample. Second harmonic generation comes from the gallium nitride particles, which have non-centrosymmetric structure. And in this case, the liquid crystal is visualized using 3-photon self-fluorescence imaging, while the particles are visualized by means of second harmonic generation signal as well, and those are the spectra that correspond to them. Again, you can see in here a colloidal particle attached to a defect in liquid crystal sample, and we can manipulate such defect structures, but also at the same time do 3-dimensional imaging and slice the sample in different imaging planes. From those, one can then visualize director structures and director fields corresponding to such samples. One more example in here is a colloidal platelet which is manipulated in a liquid crystal sample. It's an octagonal colloidal platelet, and by means of holographic laser tweezers we can also switch the type of the trapping laser beam from Gaussian to Laguerre Gaussian in the form of high intensity bright ring, as you can see in here. And with that we can rotate those particles as well as image them by means of three-dimensional optical imaging at the same time. Alright, so one more clicker question before we go for coffee, if you answer correctly. Okay, I'll have to stop in just a couple seconds because we are behind the schedule. Alright, so the most popular answer was not correct. The correct answer is none of the above. We don't really need to combine. In principle, we could do just laser tracking without using any optical imaging techniques. Anyway, I'll leave you with conclusions, and perhaps I should answer questions during the coffee break.